A star burns at the center of a vast flattened family, while scorched rocks, ocean worlds, ringed giants, frozen moons, dwarf planets, and ancient comets travel through the darkness around it. Every orbit carries a clue. Mercury hides ice beside the sun. Venus smothers beneath its clouds. Mars preserves rivers that vanished. Farther out, Jupiter commands a miniature system. Saturn turns shattered ice into beauty, and Neptune keeps a captured world moving backward through space. Beyond them, the solar system fades rather than ends. A quiet like a subscription or a share helps more calm science journeys continue. Thank you sincerely for spending this time here. What time is this playing, and where in the world is it being heard? A comment below can leave a small marker across the planet. Settle into the scale, the silence, and the slow motion of worlds. The complete tour of the solar system begins now. Long before the planets take their familiar places, the solar system begins as a dim and shapeless region within a much larger cloud of interstellar gas and dust. About 4.6 billion years ago, gravity starts drawing part of that cloud inward. The material is mostly hydrogen and helium, with a smaller share of heavier elements forged inside earlier generations of stars and scattered through space when those stars die. At first, there is no sun, no Earth, no clear boundary between one future world and another. There's only a cold mixture of particles moving in many directions, each tugging faintly on the rest. Yet the cloud is not perfectly still. It carries a small amount of overall rotation, inherited from the motions and disturbances of the surrounding galaxy. That slight spin becomes increasingly important as the cloud contracts. Gravity pulls matter closer to the center, and the shrinking cloud turns faster, just as a spinning body accelerates when its mass moves inward. This is the conservation of angular momentum, a rule that does not create the rotation but preserves and strengthens it as the cloud collapses. The young solar system therefore does not fall straight inward. It gathers, circles, collides, and slowly organizes itself around a common axis. The result is not an instant family of planets, but a broad rotating structure known as a protoplanetary disk. Its center grows dense and hot, while its outer regions remain cooler, thinner, and darker. The shape of this disk holds one of the first great clues to the architecture of the solar system. Space has 3 dimensions, so the original cloud allows particles to move above, below, and across every possible plane. Their individual paths are disorderly, and many of their orbits tilt sharply against one another. If gravity acted alone and every particle passed cleanly through the others, the cloud could remain thick and chaotic for a very long time. But matter is not perfectly transparent to matter. Dust grains strike other grains. Gas molecules collide, clumps meet, rebound, fragment, or join together. These encounters remove part of the random motion while leaving the system's overall rotation intact. Motions that carry particles upward and downward through the disk tend to cancel when oppositely directed material collides. Energy is transformed into heat and radiated away, but angular momentum remains distributed through the rotating cloud. Over time, the broad swarm becomes flatter. It does not become a perfectly thin sheet, but it settles into a disk because the disorder can fade while the shared rotation continues. The same basic process appears in many other places where gravity, rotation, and collisions act together. Rings around planets spread through narrow planes. Disks of gas surround newborn stars. Matter spiraling toward compact objects often forms flattened structures. Even spiral galaxies arrange much of their visible material into wide disks, though their full histories involve many additional forces and events. The solar system is therefore not flat because the universe prefers a decorative pattern. It is flat because collapsing matter in three-dimensional space can lose random motion through collisions while preserving a common direction of rotation. This quiet sorting process creates the stage on which planets can form. Near the center of the disk, pressure and temperature rise as more gas falls inward. The central region becomes a protostar, an object not yet powered by the same nuclear reactions that sustain the mature Sun. It glows mainly because gravitational contraction heats it. Around it, the disk continues to carry material inward, while also transporting angular momentum outward. Without that exchange, much of the gas could not approach the center. Magnetic fields, turbulence, and interactions within the disk help redistribute motion, allowing the young star to gain mass while the surrounding material spreads and evolves. Eventually, the core of the protostar becomes hot and dense enough for hydrogen nuclei to begin fusing into helium. The Sun enters the long, stable phase that defines most of its life, and its light begins to illuminate a disk already filled with the seeds of worlds. The disk is not uniform. Temperature changes dramatically with distance from the young Sun. Close to the center, heat prevents many volatile substances from freezing. Only metals and rocky minerals remain solid enough to gather efficiently. Farther out, where the disk is colder, water, methane, ammonia, and other compounds can condense as ice. This difference helps divide the future planetary system into broad regions. The inner planets grow mainly from rock and metal. The outer planets form where solid material is more abundant because ice joins dust as a building material in those colder zones. Large cores can grow quickly enough to attract thick envelopes of hydrogen and helium before the gas disk disappears. The distinction is not absolute, and material moves across the disk in complicated ways. But temperature leaves a lasting mark on planetary composition. Before planets exist, dust grains begin the slow work of construction. Tiny particles meet through gentle collisions and electrostatic attraction. Some stick. Larger aggregates then collect more material, becoming pebbles, boulders, and eventually bodies large enough for gravity to matter strongly. These growing objects are called planetesimals. They are not yet planets, but they are far more than loose dust. Some reach sizes of many kilometers. Their gravity bends nearby paths, increases collision rates, and allows growth to accelerate. The disk becomes a crowded field of bodies competing for material. Many collisions are constructive, merging objects into larger forms. Others are violent enough to break them apart. Growth and destruction occur together, and the final planets emerge from this long contest rather than from a smooth, peaceful assembly. As the largest bodies become planetary embryos, they begin reshaping the disk around them. Their gravity scatters smaller objects, clears lanes, and pulls material into new paths. Some embryos collide in giant impacts. Others are ejected from their original regions or driven inward toward the Sun. The modern solar system preserves only the survivors of this unstable era. The nearly circular, similarly aligned orbits of the major planets reveal the flat disk from which they formed, but the smaller bodies preserve more of the ancient disorder. Comets can arrive on steeply tilted paths. Asteroids occupy resonant gaps and stretched orbits. Dwarf planets beyond Neptune move through a region shaped by migration and gravitational disturbance. The system is flat in its broad design, yet never perfectly flat. Its imperfections are records of motion, collision, and loss. The planets do not simply form and remain where they began. The giant planets likely shift their orbits while the disk is still young, exchanging angular momentum with gas and with countless smaller bodies. Jupiter's immense gravity influences the asteroid belt and the growth of neighboring worlds. Neptune's movement helps organize distant icy objects into resonant paths. Such migrations can rearrange entire regions, delivering material inward and scattering other material toward the solar system's edge. Water-rich bodies from colder zones may contribute to the volatile inventory of the inner planets, though the exact history of Earth's water remains a subject of continuing study. The young system is therefore both orderly and restless. Its disk gives it a common plane and direction, but gravity ensures that every growing world affects the others. The birth of the solar system is not a single moment. It is a sequence of transitions, from diffuse cloud to collapsing core, from rotating disk to grains, from grains to planetesimals, and from planetesimals to worlds. Each stage depends on the one before it, and each leaves traces that remain observable billions of years later. Meteorites retain ancient minerals that formed near the beginning. The planets preserve differences created by distance and temperature. Orbital alignments recall the disk, while tilted axes and unusual moons recall later impacts and captures. Even the emptiness between planets is part of the story, cleared by bodies that gathered, scattered, or expelled what once filled those regions. When the disk finally thins, much of its gas is absorbed by the sun and giant planets, blown away by radiation and stellar winds, or lost into interstellar space. What remains is a young star surrounded by a structured family of planets, moons, asteroids, comets, and debris. The transformation seems almost complete, but the solar system never becomes truly still. Leftover bodies continue to collide. Orbits continue to shift. Surfaces continue to change under impacts, radiation, volcanism, and ice. The flatness of the system is therefore not the end of chaos. It is the visible memory of chaos being reduced, redirected, and preserved in a different form, out of a cloud with no planets and no clear shape. Gravity builds a rotating disk. Within that disk, collisions erase random motion while conservation laws protect the shared spin. From this balance between loss and persistence, the stage for every later world quietly appears. At the center of the solar system, the sun holds nearly all of its mass, and every planet, moon, asteroid, comet, and grain of dust moves within the reach of its gravity. It appears steady from a distance, a bright disk rising and setting with familiar regularity. Yet its quiet appearance hides a vast sphere of motion, pressure, heat, and magnetic change. The sun is not a solid object with a surface like Earth. It is a star made mostly of hydrogen and helium, held together by its own gravity and sustained by nuclear fusion in its core. Deep inside, temperatures climb to around 15 million degrees Celsius, and pressure becomes so great that hydrogen nuclei can overcome their natural electrical repulsion and join together. Through a chain of reactions, hydrogen gradually becomes helium. A small amount of mass is converted into energy, and that energy begins a long journey outward. This process has continued for about 4.5 billion years, and enough hydrogen remains for the sun to shine in a broadly stable way for billions of years more. The balance that keeps the sun stable is simple in outline and immense in scale. Gravity pulls inward, compressing the star, while hot gas and radiation push outward. Neither side completely wins. The sun remains in a state known as hydrostatic equilibrium, a continuous balance between collapse and expansion. If fusion weakened sharply, gravity would compress the core, raising its temperature and encouraging fusion to increase again. If fusion became too intense, the core would expand slightly, cool, and slow the reactions. It first enters a region where radiation carries energy outward through countless interactions. Photons are absorbed and re-emitted again and again, changing direction through dense solar material. Their outward progress is slow, and the energy that finally reaches the sun's visible layers is not carried by the same individual photons that began deep within the core. Farther out, the solar gas becomes cooler and less dense, and convection begins to dominate. Hot material rises, releases energy near the surface, cools, and sinks again. This motion forms great circulating cells and gives the visible surface a grainy texture called granulation. Each bright cell marks rising hot plasma, while darker boundaries show cooler material descending. The visible layer is called the photosphere. It is not a solid boundary, but the region from which most sunlight escapes into space. Its temperature is around 5,500 degrees Celsius, far cooler than the core but still hot enough to make the sun glow with intense white light. Above it lies a thinner layer called the chromosphere, and beyond that extends the corona, the sun's outer atmosphere. The corona is extraordinarily faint compared with the photosphere, yet it reaches temperatures of more than 1,000,000 degrees Celsius. This creates one of the sun's enduring puzzles. The outer atmosphere is much hotter than the visible surface below it. Even though it lies farther from the main source of energy in the core, magnetic waves, reconnection, and small explosive events appear to play major roles, but the detailed distribution of coronal heating remains an active field of research. The sun's magnetic field is shaped by the movement of electrically charged plasma. Because the sun is gaseous, different latitudes rotate at different rates. The equatorial regions turn faster than areas near the poles. This differential rotation twists and stretches magnetic fields, gradually storing energy. Dark sunspots appear where concentrated magnetic fields suppress the normal upward flow of heat, making those regions cooler and therefore darker than their surroundings. Sunspot numbers rise and fall in a cycle lasting roughly 11 years, while the sun's full magnetic pattern reverses over a period about twice as long, near solar maximum. The surface becomes more active, with more sunspots, flares, and eruptions. Solar flares release bursts of radiation, while coronal mass ejections can throw enormous clouds of magnetized plasma into space. They disturb the stream of charged particles already flowing from the sun and can reshape conditions across the planetary system. That continuous flow is the solar wind. It escapes from the hot corona and moves far beyond the planets, carrying the sun's magnetic influence into interplanetary space. Around Earth, the magnetic field deflects much of this charged material. Some particles enter near the polar regions and produce auroras, while stronger solar storms can disrupt satellites, radio communication, navigation systems, and electrical grids. It creates a changing space environment that reaches every world in the system. Mercury, close to the sun, endures intense radiation and a powerful solar wind. Venus receives enough energy to support an extreme greenhouse climate. Earth lies at a distance where liquid water can persist on the surface under the right atmospheric conditions. Mars receives less warmth and struggles to retain a dense atmosphere. Farther out, sunlight weakens, temperatures fall, and ice becomes a dominant material. The architecture of the solar system is shaped not only by gravity, but also by the sun's energy. In its youth, the sun is likely more active than it is now. Strong radiation and winds strip gas from parts of the protoplanetary disk and influence the early atmospheres of the planets. At the same time, the young sun is slightly dimmer overall than the present star. Earth still manages to maintain liquid water, likely because its atmosphere contains more greenhouse gases and because other climate processes compensate for the fainter sun. Across immense spans of time, the sun slowly brightens as helium accumulates in the core. The core contracts and heats, allowing fusion to proceed more rapidly. This change is gradual, but it matters for planetary climates. It evolves, and the worlds around it evolve in response. Its gravity also defines the broad order of planetary motion. Each planet is constantly falling toward the Sun while moving sideways fast enough to keep missing it. The result is an orbit. Closer planets move faster because they travel through a stronger gravitational field. Mercury completes its orbit in a small fraction of an Earth year, while Neptune requires well over a century. The Sun itself is not perfectly still at the geometric center. It shifts slightly in response to the pull of the planets, especially Jupiter and Saturn. All bodies orbit their shared centers of mass, though the Sun's dominance makes the overall system appear strongly centered upon it. Beyond the known planets, the Sun's gravity continues to hold distant icy bodies on immense orbits. Its gravitational control may extend into the remote reservoir known as the Oort Cloud, where comets can take thousands or millions of years to complete a single circuit. Yet gravity is only one boundary of the Sun's realm. The solar wind inflates a vast bubble called the heliosphere within the surrounding interstellar medium. Far beyond Neptune, the outward pressure of the solar wind weakens and meets particles and magnetic fields flowing through the galaxy. Spacecraft that travel through this boundary reveal that the solar system does not end at the orbit of the last planet. It fades gradually into a wider environment. Even from that immense distance, the Sun remains the source of the system's identity. It formed from the center of the ancient disk, gathered most of the available mass, and established the gravitational pattern around which the planets assembled. Its light sets the pace of climates and seasons. Its magnetic activity shapes the space between worlds. Its long life provides the stable time needed for complex geology and biology to emerge on at least one planet. Yet the Sun is not eternal. In the distant future, hydrogen in the core becomes depleted. Fusion shifts into surrounding layers. The star expands into a red giant, and the inner solar system is transformed. Mercury and Venus are likely engulfed, while Earth's fate depends on uncertain details of solar expansion and orbital change. Later, the Sun sheds its outer layers and leaves behind a dense white dwarf. That final state lies far beyond the present age of planets, but it is already contained within the Sun's nature. The central star is both a source of order and a moving part of a larger history. For now, it remains in the long middle phase of its life, shining with enough steadiness to make the solar system seem permanent. Beneath that steadiness, fusion continues, plasma circulates, magnetic fields twist, and energy crosses the darkness toward every surrounding world. The solar system begins in a flattened disk, but it becomes a family because the Sun holds the center, and because its gravity and light continue to bind the separate worlds into one evolving structure. Mercury is the smallest of the 8 major planets and the nearest to the Sun, a compact world moving through a region where sunlight, heat, radiation, and gravity reach unusual intensity. From a distance it resembles Earth's moon, with a grey surface covered by craters, ridges, and broad plains. The similarity is real but incomplete. Mercury is not a moon, and not a simple leftover stone. It is a planet with a dense metallic interior, a global magnetic field, cliffs that cross ancient landscapes, deposits of ice hidden in permanent darkness, and an orbital rhythm unlike that of any other major world. Its closeness to the Sun makes it difficult to observe from Earth. It never appears far from the solar glare and is usually seen only low in the sky near dawn or dusk. Spacecraft later reveal a world shaped by violent beginnings and slow contraction. Mercury travels around the Sun in about 88 Earth days, faster than any other planet. Its orbit is more elongated than those of most major planets, so its distance from the Sun changes noticeably during each revolution. At its closest approach, the Sun appears far larger and brighter in Mercury's sky than it does from Earth. Solar energy becomes fierce, yet Mercury does not remain uniformly hot. The planet rotates slowly, taking about 59 Earth days to turn once relative to the distant stars. Its rotation and revolution are locked together in a stable pattern, with 3 rotations occurring during every 2 journeys around the Sun. This arrangement is known as a spin-orbit resonance. It arises through the Sun's long gravitational influence on a planet whose shape and orbit are not perfectly circular or symmetrical. The result is a solar day of extraordinary length. From one sunrise to the next, about 176 Earth days pass. Daylight lingers for months, and night lasts just as long. During the day, surface temperatures near the equator can rise to around 430 degrees Celsius. At night, without a thick atmosphere to hold heat, the ground can fall to roughly minus 180 degrees Celsius. These are among the greatest temperature swings found on any planet. Mercury is often called the hottest planet because it lies closest to the Sun, but Venus is hotter overall. Venus possesses a dense atmosphere that traps heat through an intense greenhouse effect. Mercury has almost no atmosphere in the usual sense. Instead, it carries an extremely thin exosphere, a sparse collection of atoms released from the surface by solar radiation, the solar wind, and small impacts: sodium, potassium, oxygen, hydrogen, helium, and other particles appear within this tenuous envelope, but they rarely collide. Many are soon swept away or fall back to the ground. There is no weather, no wind moving dust across plains, and no air pressure capable of spreading warmth from the day side to the night side. The surface remains exposed to space. Meteoroids strike it directly, radiation alters its minerals, and the Sun continuously strips particles from its uppermost layers. The craters record this exposure across immense time. Some are small and sharp, while others form giant basins created by impacts energetic enough to reshape whole regions. The largest well-known impact structure is the Caloris Basin, a broad depression more than 1,000 kilometers across. The collision that forms it sends powerful seismic waves through the planet. On the opposite side, the waves may converge and help produce broken, jumbled terrain. Lava later floods parts of the basin and nearby lowlands, showing that Mercury's early history includes extensive volcanism. Smooth plains cover many older craters, while volcanic vents and irregular depressions indicate that gases once escaped from the interior. Mercury is now far quieter, but its surface preserves evidence of a world once geologically active. One of its most distinctive features is a network of long cliffs called lobate scarps. Some stretch for hundreds of kilometers and rise more than a kilometer above surrounding ground. They form as Mercury's interior cools. Cooling causes the planet to contract, reducing its diameter by several kilometers over geological time. The crust responds by breaking and thrusting one section over another. In this way, the surface becomes wrinkled by the shrinking world beneath it. These cliffs cross craters and plains, proving that contraction continues after much of the early bombardment has occurred. Smaller scarps appear relatively young, suggesting that cooling and adjustment may continue into the recent geological past. Beneath the crust lies the structure that makes Mercury exceptional among the rocky planets. Its metallic core occupies most of the planet's radius and a remarkably large share of its total mass. Earth also has an iron-rich core, but Mercury contains proportionally much more metal. The reason remains uncertain. One possibility is that a giant early collision strips away much of an original rocky mantle. Another is that intense heat near the young Sun removes lighter material before or during formation. A third is that conditions in the inner protoplanetary disk favour the assembly of metal-rich material from the beginning. No single explanation has settled the question. The core is not entirely solid. Measurements of Mercury's rotation and gravity indicate that at least part of it remains molten. Motion within this conductive liquid helps generate a magnetic field. The field is much weaker than Earth's, but its existence is surprising for such a small planet, because small worlds are expected to cool rapidly. Mercury's magnetic field creates a tiny magnetosphere that deflects part of the solar wind. The protection is limited. The Sun's magnetic environment compresses and distorts it, and charged particles can still reach the surface. The magnetosphere is a changing structure, continually pushed, stretched, and reconnected by solar activity. Mercury's polar regions provide an even quieter surprise. Because the planet's axis is tilted only slightly, the Sun stays close to the horizon near the poles. The floors of some deep craters never receive direct sunlight. In these permanently shadowed places, temperatures remain low enough for water ice to survive for very long periods. Radar observations from Earth first suggest bright deposits, and spacecraft measurements later support the presence of ice mixed with darker material. The ice may have arrived through comet and asteroid impacts, or through other processes that deliver hydrogen-bearing compounds to the surface. Molecules can move across Mercury in brief hops, released by heat and radiation, until some enter cold traps from which they rarely escape. This allows frozen water to persist on the planet nearest the Sun, not in spite of solar heat, but because local geography creates pockets of enduring darkness. Mercury is therefore a world of sharp contrasts. It has blazing plains and frozen shadows, a silent surface and an active magnetic environment, an ancient crust and signs of later contraction. Its slow rotation creates long days, while its rapid orbit carries it swiftly around the Sun. Its appearance suggests a dead moon, yet its interior preserves enough heat and motion to sustain a magnetic field. These contradictions make Mercury a valuable record of the inner solar system. Material close to the young Sun experiences conditions different from those farther out, and Mercury may preserve evidence of those early chemical and thermal boundaries. Its oversized core may reveal how planets separate metal from rock, how giant impacts alter growing worlds, or how the hottest parts of a planet forming disk sort matter before planets fully assemble. Spacecraft exploration gradually deepens this picture. Mariner 10 makes the first close passes during the 1970s and maps part of the surface. Decades later, the Messenger mission enters orbit and surveys the planet globally, measuring its chemistry, topography, gravity, magnetic field, and polar deposits. The results replace the image of a simple scorched rock with a more complex planet. Bepi Colombo, a joint mission of European and Japanese space agencies, is designed around a carefully planned journey into the Sun's deep gravitational field. Reaching Mercury is difficult because a spacecraft traveling inward must lose a great amount of orbital energy without falling uncontrollably toward the Sun. Repeated planetary flybys and long periods of solar orbit allow such a mission to adjust its path gradually. The challenge of arrival mirrors Mercury's own place in the system. It is nearby in distance, yet difficult to approach, hidden beside the overwhelming brightness of the central star. In the larger tour of the solar system, Mercury stands as the first planetary threshold beyond the Sun. It shows how quickly conditions change across a relatively small distance. Here, the solar wind is stronger, sunlight is harsher, and orbital motion is faster. Yet even in this severe environment, the planet is not reduced to a single extreme. Its history includes impact, volcanism, cooling, magnetism, and the slow gathering of ice in darkness. The smallest major planet carries a record of forces that once acted throughout the inner disk, and its battered surface remains a quiet archive beside the fire. Venus is often called Earth's sister planet because the two worlds are close in size, mass, density, and composition. Yet almost every familiar similarity ends at the top of its clouds. Beneath that pale, brilliant covering lies a surface where the air is heavy enough to crush many machines. The temperature is hot enough to melt lead, and the ground is shaped by vast volcanic plains, broken highlands, and signs of a planet that may still be changing. Venus orbits closer to the Sun than Earth, but distance alone does not explain its extreme heat. The planet is wrapped in an atmosphere made mostly of carbon dioxide, with clouds of sulfuric acid drifting high above the surface. Sunlight enters through the cloud layers, warms the ground, and is re-radiated as infrared energy. Carbon dioxide absorbs much of that escaping heat and sends part of it back downward. The result is a runaway greenhouse state, a climate in which heat becomes trapped so efficiently that the lower atmosphere settles near 460 degrees Celsius across much of the planet. Day and night differ little. Equator and poles differ less than they would on a thin-aired world. The atmosphere carries and redistributes heat with remarkable power, turning Venus into the hottest planet even though Mercury lies closer to the Sun. At the surface, pressure reaches around 90 times that of Earth's sea level, similar to the pressure found nearly a kilometre beneath Earth's oceans. Carbon dioxide there behaves as a dense, hot fluid, and the lower atmosphere moves slowly across the ground. Higher above, however, the winds become much faster. The cloud tops race around the planet in only a few Earth days, a motion known as superrotation, because the atmosphere circles Venus far more quickly than the solid planet turns. The planet itself rotates with extraordinary slowness. One full rotation relative to the distant stars takes about 243 Earth days, longer than its journey around the Sun. It also spins in the opposite direction from most major planets. On Venus, the Sun would rise in the west and set in the east, though the thick clouds would hide any clear view of the sky. The cause of this reversed rotation is uncertain. Ancient impacts may have altered its spin, while tides raised by the Sun and the dense atmosphere may also have reshaped its motion over time. The present rotation is likely the result of a long exchange among gravity, atmospheric circulation, and the internal structure of the planet. Radar is required to see through the clouds. Ordinary visible light reveals only the bright upper atmosphere, but radio waves can penetrate and return information about the hidden ground. Radar maps show that most of Venus is covered by broad volcanic plains. Thousands of volcanic structures rise above them, ranging from small domes to immense shield volcanoes. Long channels cross parts of the landscape, perhaps carved by unusually fluid lava. Circular features called coronae mark places where hot material may have risen from the mantle, lifting and cracking the crust before cooling and sinking. Mountain ranges and elevated regions interrupt the plains, including Maxwell Montes, the highest known terrain on Venus. The surface appears geologically young compared with the most ancient landscapes of Mercury, Mars, and the Moon. Large numbers of old impact craters are missing, and the craters that remain are spread in a pattern suggesting that much of the surface has been renewed during the planet's later history. For a time, one explanation imagines a global catastrophe in which widespread volcanism resurfaces nearly the entire world over a relatively brief interval. A more gradual interpretation suggests that different regions are renewed at different times through continuing volcanic and tectonic activity. The evidence does not require the whole planet to have changed in a single event, and the true history may involve episodes of intense activity separated by quieter periods. Venus has no moving system of large surface plates like those that continually reshape Earth. Its outer shell may behave as a mostly continuous lid, bending, cracking, and being altered from below without dividing into familiar drifting plates. Heat still has to escape from the interior. It may rise through mantle plumes, volcanic eruptions, local deformation, or broad overturning events. This makes Venus an important natural test of how rocky planets release internal heat when plate tectonics does not operate in the same way as it does on Earth. Signs of recent activity appear in several forms. Some volcanic features look unusually fresh in radar images. Changes observed between radar passes have been interpreted as possible alterations near a volcanic vent, and atmospheric measurements have revealed variations in sulfur-bearing gases that might reflect eruptions, changing circulation, or chemical processes in the clouds. These clues are suggestive rather than complete. The clouds conceal the surface, missions operate under severe limits, and a planet can imitate activity through processes that remain poorly understood. Even so, Venus no longer fits the old image of a world that became geologically silent long ago. It may still release heat, reshape parts of its crust, and feed gases into the atmosphere. Conditions change sharply with height. Near the surface, the atmosphere is crushing and hot. Around 50 kilometers above the ground, pressure and temperature become surprisingly similar to those near Earth's surface. It is far gentler than the landscape below. This temperate layer has drawn attention because the clouds contain droplets and complex chemical cycles. Claims of unusual gases have encouraged debate about unknown chemistry and, more cautiously, about whether any form of life could persist in such clouds. No confirmed evidence of life exists. The cloud droplets contain concentrated sulfuric acid. Water is extremely scarce, and the atmosphere is exposed to intense radiation and dynamic circulation. Any biological interpretation must come after ordinary chemical, geological, and observational explanations have been tested. The idea remains speculative, while the confirmed reality is already strange enough: a narrow altitude range with mild pressure and temperature floating above a surface that destroys landers within hours. Venus may once have been very different. Models allow the possibility that early Venus possessed liquid water and a more moderate climate, especially when the young sun was fainter. The duration of such conditions is uncertain. The planet may have remained temperate for a long period, or it may have lost its water early. As solar energy increased, evaporation could have placed more water vapor into the atmosphere. Water vapor is itself a greenhouse gas, so warming would drive further evaporation. In the upper atmosphere, sunlight would break water molecules apart. Lightweight hydrogen could then escape into space, while oxygen reacted with surface rocks or was lost through other processes. Venus today contains far more heavy hydrogen relative to ordinary hydrogen than Earth does, a sign that a large amount of lighter hydrogen has escaped. This supports a history of major water loss, though it does not reveal exactly how much surface water once existed. The absence of a strong global magnetic field may have allowed the solar wind to interact directly with the upper atmosphere, but magnetic shielding alone does not decide whether a planet keeps its air or oceans. Gravity, atmospheric chemistry, volcanic renewal, solar radiation, and time all work together. Venus retains an enormous atmosphere even without an Earth-like magnetic field, proving that atmospheric evolution depends on more than a single protective barrier. Its fate emerges from a chain of linked changes. Heat alters water, water alters heat. Escaping hydrogen changes chemistry. Volcanism adds gases. The growing sun slowly shifts the balance. What begins as a world similar in bulk to Earth becomes a climate state with no close counterpart on the present Earth. That divergence gives Venus a special place in the solar system. It shows that size and composition do not guarantee a familiar outcome. Two rocky planets can begin with similar ingredients and follow radically different paths because of distance, atmosphere, rotation, geology, and chance. Earth's climate is not mirrored on Venus, but its vulnerability becomes clearer beside it. A greenhouse effect is a normal and necessary part of Earth's warmth. Yet Venus reveals how powerful atmospheric feedback can become under very different conditions. The comparison is not a prediction that Earth will naturally become Venus. It is demonstration that planetary climates can cross thresholds and settle into states that are difficult to reverse. Beneath its unbroken clouds, Venus preserves the evidence of that transformation in volcanic plains, altered rocks, missing water, and a dense atmosphere that now governs almost every condition at the surface. It shines beautifully in Earth's sky because its clouds reflect sunlight so well. But that brightness hides one of the most severe environments among the planets. The sister world remains close in scale and distant in character, a familiar shape wrapped around an alien climate, and a reminder that neighbouring planets can carry profoundly different histories beneath nearly identical beginnings. Earth appears from space as a world of blue oceans, white clouds, dark forests, pale deserts, and slowly shifting continents. But its familiar beauty emerges from an unusually complex partnership of geology, atmosphere, water, sunlight, and life. It is the largest of the 4 rocky planets and the only known world with stable oceans spread across most of its surface. Those oceans regulate climate, carry heat around the globe, dissolve minerals, shape coastlines, and provide the setting in which life first becomes established. Yet Earth is not defined by water alone. Its interior remains active, its atmosphere is constantly renewed, and its large moon exerts a quiet influence on tides, rotation, and the long stability of the planet's axis. Together, Earth and the Moon form a linked system whose history begins in violence and matures into balance. Earth forms in the warm inner region of the young solar system, where rock and metal survive as solid grains while lighter ices are less abundant. Small bodies collide, merge, and grow into planetary embryos. The young Earth gathers mass through repeated impacts, each one adding material and releasing heat. Radioactive elements, gravitational compression, and collisions keep the interior partly molten. Dense iron and nickel sink toward the center, while lighter silicate rock rises to form the mantle and crust. This separation creates the layered planet that still exists: a metallic core, a deep, rocky mantle, and a thin outer shell. The core remains essential to Earth's magnetic field. Heat escaping from the deep interior drives motion in the liquid outer core, where electrically conducting metal circulates and generates a global magnetic field. This field forms a vast magnetosphere that redirects much of the solar wind. The magnetic field changes over time, and its poles have reversed many times in the geological past. These reversals are preserved in cooling volcanic rocks and in magnetized stripes across the ocean floor. They reveal that Earth's interior is active and that the planet's surface is not fixed. The crust is divided into large plates that move slowly over the softer upper mantle. This process, plate tectonics, continuously reshapes the world. New crust forms along mid-ocean ridges, where hot material rises and solidifies. Old oceanic crust sinks into the mantle at deep trenches. Continents collide and raise mountain ranges. Rifts open, oceans widen, and volcanic arcs grow above descending plates. Over millions of years, this movement rearranges land and sea. It also helps regulate the atmosphere by cycling carbon among rocks, oceans, living systems, and the interior. Rainwater combines with carbon dioxide and reacts with exposed rock. This slow cycle acts as a long-term climate stabilizer, though it does not prevent periods of severe warming, deep cooling, or rapid environmental change. Earth's atmosphere is another product of continuous transformation. The earliest atmosphere is likely altered or lost during violent impacts and intense solar activity. Volcanoes release water vapor, carbon dioxide, nitrogen, and other gases. As the surface cools, water condenses and fills low regions, helping create early oceans. Additional water and volatile compounds arrive in impactors, though the exact share from different sources remains uncertain. The young atmosphere contains little free oxygen. That changes after life develops forms of photosynthesis that use sunlight to build organic matter and release oxygen. At first, much of that oxygen reacts with iron and other materials. Later, it begins to accumulate in the air and oceans, transforming surface chemistry and allowing an ozone layer to form high in the atmosphere. Oxygen eventually supports complex life, but its rise unfolds through biological innovation, geological change, and repeated shifts in the balance between production and removal. Life becomes part of Earth's planetary machinery. Microorganisms alter oceans and rocks, plants change soils, weathering rates, and atmospheric composition. Marine organisms build reefs and produce sediments that become limestone. Living systems respond to climate while also influencing it. Earth is therefore not merely a planet where life exists. Its air, surface, and chemistry have been deeply modified by life over billions of years. Habitability also depends on physical conditions. Earth orbits at a distance where sunlight permits liquid water under a suitable atmosphere. Its gravity retains substantial air without turning the planet into a small gas world. Its rotation produces a regular cycle of light and darkness, while its axial tilt creates seasons without making them overwhelmingly extreme. The Moon plays a role in preserving that axial behavior. It is unusually large compared with Earth, measuring more than a quarter of Earth's diameter. Most leading explanations trace its origin to a giant impact early in solar system history. A large planetary body strikes the young Earth, throwing hot rock into orbit. Much of that debris gathers into the Moon. The precise geometry, speed, and composition of the collision remain subjects of study, but lunar samples show close chemical similarities with Earth, consistent with a shared and heavily mixed history. In its earliest state, the Moon is far closer to Earth than it is now. It appears much larger in the sky, and raises stronger tides in the young oceans and in Earth's partly molten crust. Tidal friction transfers angular momentum from Earth's rotation to the Moon's orbit. Earth's spin gradually slows, lengthening the day, while the Moon moves outward by a few centimeters each year. The Moon keeps nearly the same face turned toward Earth because its rotation period matches its orbital period, a state called tidal locking. Long ago, it rotates more quickly, but Earth's gravity raises tidal bulges within it. Internal friction slows the rotation until one turn matches one orbit. Earth is also affected by lunar tides. The oceans rise and fall as the gravitational pulls of the Moon and Sun act across the planet. Coastlines and ocean depth make local tides complicated, but the underlying cause is the difference in gravitational force across Earth's diameter. Water on the side facing the Moon is pulled slightly more strongly than Earth's centre, while Earth's centre is pulled more strongly than water on the far side. This creates two broad tidal bulges, which the rotating planet carries through changing coastlines. Tides shape shore environments, mix nutrients, influence marine ecosystems, and may have affected settings in which early life adapts to changing water levels. The Moon also helps limit large variations in Earth's axial tilt without its stabilizing influence. Gravitational interactions with other planets could cause the tilt to wander more dramatically over long timescales. Earth's climate would still be governed by many factors, but greater changes in tilt could produce more extreme shifts in the distribution of sunlight. The Moon does not hold the axis perfectly still. Earth slowly wobbles like a spinning top, and its tilt changes within a limited range. Yet the Moon helps keep the variations relatively restrained, giving Earth a more stable background for oceans, climates, and ecosystems to persist through deep time. The Moon itself is an archive of the early solar system, with no thick atmosphere, flowing water, or active plate tectonics. Its surface preserves impact scars far older than most landscapes on Earth. The dark plains visible from Earth are ancient lava fields that fill enormous impact basins. The brighter highlands are older, heavily cratered terrain. Lunar rocks reveal volcanic activity, a once molten outer layer, and a long decline as the small world loses internal heat. Water ice survives in permanently shadowed polar craters, sheltered from sunlight in conditions similar to cold traps on Mercury. These deposits may contain material delivered by comets, asteroids, and the solar wind. They also preserve clues about the movement of water through the inner solar system. Earth hides much of its earliest history because its surface is continually recycled. Mountains erode, crust sinks, sediments bury older rocks, and living processes alter chemistry. The Moon preserves what Earth erases. Together, the two worlds provide a fuller record. Earth shows the power of change, while the Moon records what remains when change slows. Their partnership continues in every tide, every gradual lengthening of the day, and every centimetre of lunar retreat. Earth's habitability does not arise from one perfect condition. It grows from a network of interacting systems that remain dynamic rather than fixed. Oceans store heat, the atmosphere moves it. Plate tectonics cycles material. The magnetic field responds to the core. Life changes the air, and the Moon moderates the long rhythm of rotation and tilt. None of these systems guarantees stability forever, and each has changed greatly through time. Yet together they create a planet capable of remaining wet, geologically active, and biologically productive across billions of years. In the quiet space between Earth and the Moon, the history of a giant impact has become a lasting balance, and a violent beginning continues to shape the calm blue world below. Mars stands beyond Earth as a smaller, colder world, whose surface holds the outlines of rivers that no longer flow. From orbit, it appears rust-red because iron-bearing minerals in its soil have reacted with oxygen over immense spans of time. Dark plains, enormous canyons, cratered highlands, and bright polar caps divide its face into familiar and remote regions. Mars has mountains, valleys, seasons, clouds, winds, frost, and a day only slightly longer than Earth's. Yet its atmosphere is thin, its surface is dry, and liquid water cannot remain stable for long under present conditions. The contrast between the modern planet and the landscapes carved into it creates one of the central mysteries of the solar system. Mars today looks like a desert, but much of its geology records a wetter past. The planet forms from the same inner disk of rock and metal that builds Mercury, Venus, and Earth, but its smaller size shapes everything that follows. Mars has less mass and weaker gravity. Its interior cools more quickly, and its atmosphere is easier to lose. Even so, the young planet is active. Volcanoes erupt, impacts excavate deep basins, and heat flows through its crust. Some of the largest volcanic structures in the solar system rise on Mars. Olympus Mons towers above the surrounding plains, built by repeated lava flows that accumulate over a very long time. The volcano becomes so large partly because Mars does not have plate tectonics like Earth. On Mars, the crust remains relatively stationary above sources of rising magma, allowing one mountain to grow repeatedly in the same place. Nearby, the Tharsis region forms a broad uplift covered by giant volcanoes and fractured terrain. Far from these heights, Valles Marineris opens as a canyon system stretching thousands of kilometers. Tectonic stretching, faulting, collapse, landslides, and later erosion create a complex wound across the surface. Layered deposits and channels within it show that water and ice later modify parts of the landscape. The strongest evidence for ancient water lies in the oldest terrain. Branching valley networks descend through cratered highlands, resembling river systems shaped by rainfall, snowmelt, or groundwater. Some channels converge into basins where standing water may once have collected. Fan-shaped deposits spread where flowing water slows and releases sediment. Layered rocks appear in places where lakes may have persisted long enough to gather mud, sand, salts, and organic material. Minerals that form in the presence of water occur across wide regions, including clays that usually develop under relatively mild chemical conditions. These features do not all belong to the same climate or moment. Some may form during long wet intervals, while others may result from brief episodes triggered by volcanism, impacts, orbital changes, or the melting of buried ice. The evidence supports repeated interaction with liquid water, but the duration and global extent of warm conditions remain uncertain. The ancient sun shines more faintly than it does now, making early warmth difficult to explain. Mars receives less solar energy than Earth, so a thicker greenhouse atmosphere is likely needed to keep water liquid across broad areas. Carbon dioxide is released by volcanoes and may once have been much more abundant. Other gases, clouds, and dust may also contribute to warming. Yet climate models often struggle to produce a continuously warm planet with stable oceans and rivers. Early Mars may instead alternate between long cold periods and shorter episodes of melting. Ice can accumulate at the surface or underground, then melt when orbital changes, volcanic gases, impacts, or other shifts briefly raise temperatures. Rivers and lakes can form during these intervals, leaving permanent marks even if favorable conditions are brief. The surface preserves the results more clearly than it preserves the climate that creates them. Mars may once hold a northern ocean, though the evidence remains debated. The northern plains are lower and smoother than the southern highlands, and some features have been interpreted as ancient shorelines. Large channels empty toward the north, suggesting that water released from underground or melted from ice may have pooled there. Yet proposed shorelines are uneven. Later deformation complicates the terrain, and some smooth deposits can form without an ocean. A vast body of water is possible, but smaller seas. Regional lakes, buried groundwater, glaciers, and repeated floods may also explain much of the record. Water once moves across and within Mars on a scale far beyond anything occurring on the surface today. Over time, the planet changes. Its interior cools, volcanic activity declines, and the magnetic field generated by its core weakens. Ancient rocks preserve signs that Mars once possesses a global magnetic field, but that protection disappears early. Without a strong planetary field, the upper atmosphere interacts more directly with the solar wind. Charged particles and ultraviolet radiation help strip atoms into space, especially when the young sun is more active. Mars also loses atmosphere because of its weaker gravity, impacts, and chemical reactions that lock gases into rocks and polar deposits. No single process removes everything. Atmospheric loss is gradual and tied to the changing sun and planet. As pressure falls, liquid water becomes less stable at the surface. It freezes, evaporates, or boils at temperatures where it would remain liquid on Earth. Some escapes to space after sunlight breaks water molecules apart. Some becomes trapped as ice in the polar caps, beneath the soil, and within buried glaciers. Some reacts with minerals and becomes bound into the crust. The vanished rivers do not point to water disappearing in one sudden event. They point to water changing form and location. Modern Mars still contains a great deal of it. The polar regions hold layered deposits of water ice mixed with dust, while seasonal caps of frozen carbon dioxide grow and shrink. Buried ice appears across middle and high latitudes, sometimes beneath only a shallow layer of soil. Smooth flowing shapes around cliffs resemble glaciers covered by rock. Fresh impact craters expose bright ice beneath the surface, proving that frozen water lies close to the ground in some regions. Hydrated minerals preserve water within their crystal structures. Deep underground, higher pressure and heat may allow salty liquid to exist in pores or isolated reservoirs, though strong claims for present subsurface lakes remain disputed. The planet is dry at the surface, not empty of water. Its water survives mainly as ice, vapor, and chemically bound material. The atmosphere today is composed mostly of carbon dioxide and has less than 1% of Earth's sea level pressure. Thin clouds of water ice drift through the sky. Dust devils cross the plains, and global dust storms sometimes spread until much of the planet is veiled. Temperatures can rise above freezing under favorable daytime conditions, but low pressure causes exposed liquid to evaporate or freeze quickly. Dark streaks that appear seasonally on steep slopes once seemed like possible flows of salty water. Later studies show that dry grains sliding downhill can explain much of their behavior, although small amounts of moisture may still influence surface chemistry. Its landscapes look familiar enough to invite comparison with Earth, but its environment follows different rules. The search for life therefore focuses heavily on the past and on protected environments. Ancient lakes may have offered liquid water, useful chemical elements, and sources of energy. Rovers explore sediments where these conditions once overlap. Curiosity finds that Gale Crater contains a long-lived lake environment with clay minerals and organic molecules preserved in rocks. Perseverance studies Jezero Crater, where a river delta records the delivery of sediment into an ancient lake. Organic molecules are not proof of life, because they can form through non-biological chemistry and arrive in meteorites. Habitability is not habitation. The evidence shows that some Martian environments could once support known forms of microbial life, not that life definitely appears there. Any surviving organisms today would likely need shelter from radiation, dryness, and chemical oxidants at the surface. The subsurface offers more stable temperatures and possible access to ice or brines, but it remains largely unexplored. Mars is therefore a world defined by traces rather than by certainty. Dry channels trace lost flows. Mineral layers trace vanished lakes. Escaping atoms trace a thinning atmosphere. Buried ice traces climates that shift as the planet's axis changes over long time scales. The planet is not a failed Earth, because it follows its own history from the beginning. Its lower mass, early cooling, atmospheric loss, and orbital setting create a different path. Yet the resemblance remains powerful because water once shapes both worlds. On Earth, rivers continue to erase and renew the surface. On Mars, the rivers stop and their valleys become fossils of climate. The red planet carries those fossils across silent plains, holding the memory of a time when water moves beneath a thicker sky, and the boundary between habitable and barren is far less clear than it appears today. Between Mars and Jupiter lies a region often described as a belt of rubble, but the name creates the wrong impression. The asteroid belt is not a crowded wall of rocks drifting shoulder to shoulder. It is an immense volume of space in which most objects are separated by vast distances, and a spacecraft can pass through without weaving between constant hazards. What fills this region is not a failed planet broken into fragments after destruction, but a surviving population of ancient bodies that never assembled into a single world. Their growth is interrupted by the gravity of Jupiter, by collisions, and by the changing architecture of the young solar system. The belt therefore preserves both construction and failure. Its asteroids are remnants of the same early process that builds the planets, but they remain small enough to retain materials and structures that larger worlds erase through melting, differentiation, volcanism, and tectonic renewal. The largest object within it is Ceres, a dwarf planet with enough gravity to pull itself into a rounded shape. Ceres contains roughly a quarter of the belt's total mass, yet it is still far smaller than Earth's moon. Around it move millions of smaller objects, from bodies hundreds of kilometers across to stones, dust, and fragments created by repeated impacts. Most of the belt's mass is concentrated in only a few large objects, including Vesta, Pallas, and Hygeia. Even if all known asteroids there could somehow merge, the result would still be much smaller than Earth. This low mass helps explain why the region never becomes a full-sized world. But the deeper cause lies in the gravitational influence of nearby Jupiter. As planetesimals form in the disk, collisions can make them grow. Yet Jupiter becomes massive early and disturbs the paths of bodies beyond Mars. Instead of meeting gently, many collide at speeds that shatter rather than merge. Resonances with Jupiter repeatedly tug on asteroids at particular orbital distances. A resonance occurs when the periods of two orbiting bodies form a simple relationship, allowing small gravitational pulls to accumulate. In the asteroid belt, these effects clear gaps known as Kirkwood gaps. Objects that enter some resonant paths can have their orbits stretched until they cross those of Mars or Earth, or until they are thrown toward the outer solar system. Some meteorites that fall on Earth begin as fragments in the asteroid belt. A collision exposes them. Sunlight and thermal forces gradually alter their orbits, and planetary resonances deliver them into paths that cross Earth. These meteorites carry minerals older than any surviving rocks on Earth's active surface. Some contain tiny inclusions that condensed near the beginning of solar system history. Their ages help establish when the protoplanetary disk first forms solid material. Others come from bodies that heat enough to separate into metallic cores and rocky mantles. Iron meteorites may be pieces of shattered cores, while certain stony meteorites preserve crusts or mantles from early differentiated asteroids. The belt contains both primitive objects that remain chemically close to the original disk and altered objects that once become miniature worlds. Some are dark and rich in carbon-bearing compounds. Others are brighter and dominated by silicate rock. A smaller group contains high proportions of metal. The young planets migrate, and smaller bodies are scattered across wide distances. Materials associated with colder outer regions can enter the belt, while warmer inner materials can move outward. The belt becomes a mixed collection, assembled through motion as much as through local formation. Ceres reflects this mixture. Its low density and surface chemistry indicate that it contains substantial water ice, along with rock and salts. Beneath its dusty exterior, ice may form a large part of the crust, and deeper layers may preserve brines or residues from an ancient internal ocean. Ceres is round because its gravity overcomes the strength of its materials and draws them toward equilibrium. Yet its surface is heavily cratered and geologically subdued. It is larger and more complex than an ordinary asteroid, but too small to clear its orbital neighborhood and become a major planet. Size brings gravity. Gravity brings internal pressure, and internal heat allows materials to separate, move, and react. One of the most striking features on Ceres lies within a crater, where brilliant deposits stand out against the dark ground. These bright areas are rich in salts. They likely form when salty liquid or slushy material rises from below and reaches the surface, where water escapes and leaves reflective minerals behind. Some deposits appear geologically young, suggesting that brines persist beneath the crust long after the main period of planetary formation. Ahuna Mons, a solitary mountain with smooth flanks, may be a cryovolcano, a structure built from ice-rich material that rises and freezes. Ceres is therefore not simply inert. It may remain capable of slow internal activity driven by salts, residual heat, and the behavior of water under pressure. Vesta offers a different story. It is smaller than Ceres, but denser and more strongly shaped by early melting. Radioactive elements in the young solar system release enough heat to differentiate Vesta into a crust, mantle, and metallic core. A vast impact near its south pole excavates deep material and sends fragments into space. Some of those fragments become a recognizable family of asteroids, and some eventually reach Earth as meteorites. Through them, Vesta becomes one of the few planetary bodies that can be studied both by spacecraft and by samples already present in laboratories. It resembles a world whose development begins strongly but is cut short before it can become large. The contrast between Vesta and Ceres captures the belt's variety. Vesta is relatively dry, rocky, and differentiated. Ceres is richer in water and salts, with signs of icy geology. They may form in different parts of the early disk, or gather different mixtures of material before taking their present orbits. Smaller asteroids add further complexity. Many are not solid monoliths but rubble piles, loose collections of fragments held together by weak gravity. Their shapes can be irregular, their surfaces covered in boulders and dust, and their interiors filled with empty spaces. A collision may break a parent body apart without scattering every piece forever. Gravity slowly gathers some fragments back into a new object. Such asteroids can spin, shed material, or be reshaped by later impacts. Sunlight also changes their rotation and orbits through subtle effects. When an asteroid absorbs sunlight and later releases the energy as heat, the tiny push can alter its path over millions of years. Uneven heating can change spin rates until loose material moves toward the equator or escapes. These gradual forces matter because asteroid gravity is so weak. Asteroids also matter because some approach Earth. Near-Earth asteroids are not confined to the main belt. Their orbits bring them closer to the Sun and sometimes across the paths of terrestrial planets. Most present no immediate danger, and known objects are tracked to refine their future positions. Impacts are natural events that have occurred throughout Earth's history, ranging from harmless particles burning in the atmosphere to rare large collisions capable of global consequences. The same population that poses a hazard also carries scientific interest. Asteroids preserve water-bearing minerals, metals, and primitive organic compounds. Sample return missions show that small bodies contain complex material from the early solar system, including ingredients relevant to the chemistry that precedes life. This does not mean asteroids carry living systems to Earth, but they can deliver water, carbon-rich molecules, and minerals that influence a young planet's surface chemistry. The belt stands as a boundary between the rocky inner worlds and the giant planets, yet it is also a bridge. It contains material linked to both regions, stirred together by migration and resonance. Its empty spaces reveal Jupiter's power, while its surviving bodies reveal the disk that exists before Jupiter fully reshapes it. Ceres preserves ice in a zone where warmth and cold meet. Vesta preserves the interior of a small differentiated world. Meteorites preserve the ages and chemistry of the first solids. Broken families preserve ancient collisions. Nothing in the belt is large enough to dominate the region, But together these bodies form a distributed record of planetary formation. The planets tell the story of successful growth. The asteroid belt tells the story of interrupted growth, and in that interruption, the solar system leaves many of its oldest pages unburned. Jupiter dominates the outer solar system with a presence so large that it seems less like a planet among others, and more like the centre of a smaller system nested within the larger one. Its mass is greater than that of all the other planets combined, and its gravity shapes the paths of asteroids, comets, moons, and even neighbouring planets. Yet Jupiter has no solid surface on which a spacecraft could land. It is a giant sphere made mostly of hydrogen and helium, wrapped in clouds, storms, lightning, and powerful winds. Its visible bands drift in alternating directions, while deeper layers move under pressures that transform familiar gases into exotic states. Around it circles a family of moons so diverse that several resemble independent worlds, with oceans, volcanoes, ice, and histories of their own. The rocky planets are small, dense, and surface-dominated, while Jupiter is vast, fluid, and defined by atmosphere, rotation, magnetism, and gravity. It forms beyond the colder region of the young protoplanetary disk, where water and other volatile compounds can freeze into solid material. This allows a large core to grow more quickly than it could in the warmer inner system. Once that core becomes massive enough, it attracts enormous quantities of hydrogen and helium before the surrounding gas disk disappears. Some models begin with a solid core that gradually gathers gas, while others allow parts of the disk to collapse more directly under gravity. Jupiter's interior structure may preserve evidence of both rapid growth and later mixing, because the boundary between a distinct core and the overlying planet may be blurred. Heavy elements appear spread through a broad central region rather than confined within a simple compact sphere. The planet may have absorbed planetesimals or experienced a major impact during its youth. Jupiter grows early enough to influence the development of the entire solar system. Its gravity can scatter smaller bodies, limit the growth of Mars, disturb the asteroid belt, and or alter where material accumulates. Jupiter is not merely one result of planetary formation. It is an agent that helps determine the results around it. The visible atmosphere offers only the uppermost expression of this deep world. Bright zones and darker belts wrap around the planet in broad stripes. Their colours come from cloud layers and trace compounds whose chemistry is changed by sunlight, heat, and vertical motion. Ammonia ice forms high clouds, while deeper layers may contain ammonium hydrosulfide and water. Air rises in some bands, cools, and forms bright clouds. In neighbouring bands, material sinks, revealing darker depths. Powerful jet streams separate these regions and flow eastward or westward at high speed. Jupiter rotates once in about 10 hours, faster than any other planet, and this rapid spin shapes its atmosphere into long bands instead of allowing storms to spread freely across latitude. The same rotation flattens the planet slightly, widening its equator and compressing its poles. The Great Red Spot is the most famous of its storms, a giant rotating system that has persisted for centuries. It is larger than Earth, though measurements show that it has been shrinking over time. Its winds circle around a high-pressure region, and its reddish colour may come from chemical compounds lifted from deeper layers and altered by sunlight. Other storms form, merge, fade, and reappear. White ovals, brown barges, and turbulent wakes fill the spaces between jet streams. Near the poles, groups of cyclones form remarkable geometric arrangements, with one central storm surrounded by others. These patterns reveal a restless fluid planet releasing heat from within. Jupiter emits more energy than it receives from the Sun. Part of this heat remains from its formation. and part is produced as the planet slowly contracts under gravity. The interior is so compressed that hydrogen behaves in ways impossible near Earth's surface. Deeper down, pressure forces hydrogen into a liquid metallic state in which electrons move freely. This electrically conducting fluid, combined with rapid rotation, generates Jupiter's immense magnetic field. The resulting magnetosphere is the solar system's largest planetary magnetic structure. It traps charged particles and creates intense radiation belts that can damage spacecraft electronics and would be hazardous to unprotected life. The field extends far into space, compressed on the side facing the Sun and stretched into a long tail on the opposite side. Auroras glow near Jupiter's poles as charged particles follow magnetic field lines into the upper atmosphere. Many originate within Jupiter's own moon system, Io, the innermost of the 4 large Galilean moons, supplies vast amounts of sulfur and oxygen through its volcanic activity. Jupiter's magnetic field sweeps this material into a torus of plasma that circles the planet and links the moon to the wider magnetosphere. Io is the most volcanically active known world. Its surface is covered with sulfur compounds, lava flows, calderas, and plains that are renewed so quickly that few impact craters remain. The energy driving this activity comes mainly from tides. Io follows an orbit made slightly elliptical through gravitational interactions with Europa and Ganymede. As its distance from Jupiter changes, the giant planet's pull flexes the moon repeatedly. Rock bends, friction generates heat, and the interior partially melts. Volcanoes then erupt plumes hundreds of kilometers above the surface. Io demonstrates that a small world can remain intensely active without relying mainly on radioactive heat. Orbital relationships can serve as an engine, Europa, moving farther out. Appears quieter at first glance. Its surface is bright, icy, and crossed by dark lines and ridges. Few large craters are visible, suggesting that the surface is geologically young. Beneath the ice, strong evidence points to a global ocean of liquid water. Tidal flexing supplies heat. While salts and other materials may keep the ocean from freezing completely, the ice shell may crack, shift, and slowly recycle, allowing limited exchange between the surface and the water below. Europa therefore becomes one of the most important places in the search for habitable environments beyond Earth. Liquid water, chemical elements, and energy may coexist there. This does not establish life, and the thickness of the ice, the ocean's chemistry, and contact with the rocky seafloor remain uncertain. Ganymede, the largest moon in the solar system, is bigger than Mercury though less massive. It is a mixture of rock and ice and appears to contain a deep ocean buried between layers of high-pressure ice. Ganymede generates its own magnetic field, probably through motion in a liquid metallic core. Its ancient dark terrain is heavily cratered, while younger bright regions are cut by grooves and ridges. These landscapes indicate that the crust has been stretched and reshaped, perhaps as internal layers froze, expanded or shifted. Ganymede orbits within Jupiter's larger magnetic environment, so its own field forms a small magnetosphere inside a much greater one. Callisto, the outermost Galilean moon, has a surface saturated with impact craters. It appears far less geologically active than its companions because tidal heating is weaker at its greater distance. Its ancient crust preserves scars accumulated across billions of years, including enormous multi-ring impact structures. Even Callisto may hide a subsurface ocean kept liquid by salts and internal heat. Together, the 4 Galilean moons form a sequence of changing conditions with distance. Io is dominated by tidal fire. Europa carries an ice-covered ocean. Ganymede combines great size, internal differentiation, and magnetism. Callisto preserves ancient impact history in relative quiet. Beyond them circle dozens of smaller moons, many with irregular shapes and distant tilted or reversed orbits. Some likely formed near Jupiter, while others were captured after approaching the planet. Collisions may have broken larger captured objects into families that now share similar paths. Jupiter also possesses faint dusty rings that may be continually renewed by impacts on small inner moons. Dust knocked from these bodies spreads into thin bands under the influence of gravity, sunlight, and magnetism. The planet's family is therefore not static. Material moves between moons, rings, plasma, and atmosphere. Impacts create dust. Volcanoes feed charged particles into magnetic space. Resonances exchange energy among orbits. Jupiter binds the system, but its gravity also stresses, heats, scatters, and transforms what it holds. Seen in this way, Jupiter is both a planet and an environment, a vast rotating structure within which many smaller worlds evolve. Its storms reveal the behavior of deep atmospheres. Its interior reveals matter under extreme pressure. Its magnetic field creates a radiation domain larger than the Sun itself appears from Earth's sky. Its moons show that geology and possible habitability do not require a planet to orbit a star directly. Around the largest planet, the solar system repeats some of its own complexity on a smaller scale, and the boundary between planet and system quietly begins to blur. Saturn is recognized before any telescope reveals its nature, a pale point of light moving slowly among the stars. But magnification transforms it into one of the most extraordinary sights in the solar system. A broad system of rings surrounds the planet, bright enough to appear solid from a distance and delicate enough to vanish almost entirely when seen edge-on. Beneath them lies a giant world of hydrogen, helium, storms, winds, and deep pressures, while beyond them moves a varied family of moons shaped by ice, tides, impacts, and hidden oceans. Saturn is not simply Jupiter with rings. It is less massive, less dense, and more visibly defined by the structures around it. Its average density is lower than that of water, though no ocean could hold a world of such scale, and its rapid rotation gives it a strongly flattened shape. The planet turns in roughly 10.5 hours, causing its equator to bulge and its poles to compress. Pale bands wrap around its atmosphere, usually softer in contrast than Jupiter's, yet powerful jet streams move within them, and enormous storms can rise from depths hidden beneath layers of cloud. Saturn's upper atmosphere contains ammonia ice, with deeper clouds likely formed from other compounds and water. Hydrogen dominates the planet, and pressure transforms it as depth increases. Far below the visible clouds, hydrogen becomes liquid, and deeper still it may enter a metallic state capable of conducting electricity. Saturn's magnetic field is generated within this interior, but it differs from Jupiter's in an unexpected way. It is remarkably aligned with the planet's rotation axis. Most planetary magnetic fields are tilted, making their rotation easier to measure from repeating radio signals. Saturn's near alignment complicates that measurement and suggests that processes within its deep interior may be organized in a distinctive way. The field creates auroras and traps charged particles, while interaction with the solar wind forms a broad magnetosphere. Yet the rings and moons continually influence this magnetic environment, adding dust, gas, and charged material. The atmosphere itself releases more energy than Saturn receives from the Sun. Some comes from slow gravitational contraction, and some may come from helium separating from hydrogen and sinking inward. This helium rain releases energy as it falls, adding warmth to the deeper planet. Saturn therefore glows faintly with stored and generated heat, Even at a distance where sunlight is weak, its weather can still become violent. At intervals of roughly one Saturn year, a vast white storm erupts and spreads around much of the planet. Smaller storms, vortices, and wave patterns move through the cloud bands, while winds near the equator reach extraordinary speeds. At the North Pole, a six-sided jet stream surrounds a central cyclone. The hexagon is not a solid object but a stable wave pattern in the atmosphere, maintained by differences in wind speed and the behavior of a rapidly rotating fluid. At the South Pole, another great vortex reveals deeper cloud layers in its eye. These polar structures show that geometry can emerge naturally from flowing gases without any need for rigid boundaries. Above all, however, Saturn is defined by its rings. They stretch across hundreds of thousands of kilometers while remaining astonishingly thin compared with their width. The main rings are composed mostly of water ice, with particles ranging from dust grains to boulders and larger fragments. Their brightness comes from countless icy surfaces reflecting sunlight. From far away they blend into smooth bands, but close observation reveals gaps, narrow ringlets, waves, clumps, and changing textures. The rings do not behave like a solid disk. Each particle follows its own orbit around Saturn. Material closer to the planet moves faster, while material farther away moves more slowly. This differential motion allows the rings to spread and shear, yet gravity organizes them into patterns. Moons embedded within or near the rings open gaps, confine narrow bands, and raise spiral waves. Some small moons act as shepherds, their gravity keeping ring edges sharply defined. Other patterns arise from orbital resonances with larger moons farther away. When a ring particle is repeatedly tugged at the same point in its orbit, small effects accumulate, creating gaps or density waves that can travel through the ring material. The Cassini division, visible even through modest telescopes, is not completely empty, but contains much less material than neighbouring rings. It is shaped strongly by resonance with the moon mimas. Smaller gaps reveal the influence of tiny moons, some discovered because of the structures they create before they are seen directly. The rings are therefore a laboratory for orbital mechanics, displaying in miniature the same processes that shape protoplanetary disks, asteroid belts, and systems around other stars. Their origin remains uncertain. One possibility is that they are remnants of a moon torn apart by Saturn's tides after moving too close. Another is that collisions break apart icy moons or comets, feeding debris into orbit. The rings may contain both ancient and younger material, and their present brightness does not give a simple age. Dust from interplanetary space gradually darkens ice, while collisions expose fresh surfaces and redistribute material. Measurements indicate that the main rings contain far less mass than once imagined, perhaps comparable to a modest icy moon. Material is also falling from the rings into Saturn's atmosphere in a process known as ring rain. Charged water products and dust follow magnetic field lines downward, while other particles drift inward through collisions and drag. This means the rings are changing and may not survive in their current form forever. Yet estimating their remaining lifetime depends on uncertain rates and on processes that can renew or rearrange them. Their beauty is not static. It is a passing configuration within a long history of breakup, capture, erosion, and renewal. The moons beyond the rings extend that history into separate worlds. Titan, the largest, is bigger than Mercury and wrapped in a dense atmosphere rich in nitrogen. Orange haze hides its surface from visible light. Radar reveals dunes, river channels, broad plains, and lakes and seas of liquid methane and ethane near the poles. Titan's cold climate allows hydrocarbons to play a role similar to water on Earth. Methane evaporates, forms clouds, falls as rain, flows through channels, and gathers in basins. Beneath the icy crust, a deep ocean of liquid water may persist. Titan therefore contains two very different fluid systems, one on the surface based on hydrocarbons and one hidden below based on water. Its atmosphere also hosts complex organic chemistry as sunlight and charged particles break apart nitrogen and methane. Larger molecules form and settle as haze, coating the surface with carbon-rich material. These compounds are not evidence of life, but they make Titan an important place for studying chemistry that can grow complex before biology begins. Enceladus is far smaller, yet its significance is equally great. Bright ice covers its surface, and long fractures cross the South Polar region. From these cracks, jets of water vapor, ice grains, salts, and organic compounds erupt into space. The material comes from a global ocean beneath the crust and feeds Saturn's diffuse outer ring. Tidal flexing provides heat as Enceladus moves through an orbit influenced by nearby moons. Evidence within the plume suggests interaction between liquid water and warm rock on the seafloor. This creates chemical gradients that could provide energy in a habitable environment. No life has been detected, but Enceladus allows material from a hidden ocean to be sampled without drilling through ice. Mimas, with its enormous impact crater, appears inactive but may also conceal internal water. Tethys, Dione, and Rhea preserve mixtures of old craters, bright fractures, and signs of past geological change. Iapetus has one dark hemisphere and one bright hemisphere, partly because dust from distant moons settles on its leading side and temperature differences then strengthen the contrast. A great ridge circles much of its equator, giving the moon a shape unlike any other known body. Hyperion tumbles chaotically in its orbit, while Phoebe moves on a distant backward path that suggests capture. Saturn's family is a record of formation and disruption at many scales. Some moons gather from the original disk around the planet. Others may be captured. Some break apart to feed rings, while ring material may also gather into small moons near the edges. Tides move moons outward or inward. Resonances exchange energy, and collisions alter surfaces. The planet, rings, and moons cannot be understood separately because each continually reshapes the others. Saturn appears serene from afar, suspended within luminous bands, but the serenity comes from countless moving fragments, following precise gravitational paths. Ice collides softly. Moons carve waves. Hidden oceans flex. Storms circle the poles, and ring particles slowly fall into the atmosphere. The system's elegance is not the absence of change. It is change arranged into patterns so vast and regular that motion itself becomes structure. Uranus enters the outer solar system as a pale blue globe with an almost featureless face. Quiet in appearance, yet deeply unusual in motion. It is the seventh planet from the Sun, a cold giant whose atmosphere contains hydrogen, helium, and methane, and whose entire system seems to have been turned onto its side. Its axis is tilted by about 98 degrees, so the planet rotates almost sideways as it travels around the Sun. Instead of standing broadly upright like Earth or Jupiter, Uranus rolls along its orbit with one pole leaning toward the Sun for part of its long year. This extreme tilt shapes its seasons, its rings, its magnetic field, and the arrangement of its moons. It also preserves the memory of an ancient disruption, perhaps a giant impact or a more complicated series of encounters during the solar system's youth. Uranus belongs to a class often called the ice giants, along with Neptune. The name does not mean that the planet is a frozen solid. It means that a larger share of its interior is made from substances such as water, ammonia, and methane, described as ices because they condense at low temperatures in the outer protoplanetary disk. under the pressure and heat inside Uranus. These materials exist as hot, dense fluids rather than ordinary blocks of ice. Above them lies an atmosphere dominated by hydrogen and helium, while deeper regions may surround a rocky core. The boundaries are probably gradual and mixed, not perfectly separate shells. Uranus is smaller than Jupiter and Saturn, but still enormous compared with Earth. Its diameter is about 4 times Earth's, while its mass is more than 14 times greater. Yet its average density is relatively low, reflecting a composition rich in light gases and volatile compounds. The upper atmosphere gives Uranus its blue-green colour. Methane absorbs red light from sunlight and allows more blue and green wavelengths to return to space. Beneath the calm colour, the atmosphere contains bands, winds, clouds, and storms. Although many are subtle in visible light, infrared observations reveal more structure than early images suggest. Bright clouds appear where methane ice condenses, and dark features may mark deeper vortices similar in broad form to storms on Neptune. Winds move rapidly around the planet, with some flowing in the direction of rotation and others against it depending on latitude. The planet rotates once in roughly 17 hours, fast enough to flatten it slightly at the poles. The tilt makes seasonal change extreme. Uranus takes about 84 Earth years to complete one orbit. For around a quarter of that time, one pole points broadly toward the Sun while the opposite pole remains in darkness. Each pole therefore experiences continuous daylight followed by continuous night, with transitions lasting for years. Near the equinoxes, sunlight reaches the equatorial regions more directly, and day and night alternate in a more familiar pattern. These unusual seasons do not simply make one pole much hotter than the other. The atmosphere redistributes energy, and the planet's response is delayed by its great depth. Some cloud activity increases as seasonal geometry changes, but the exact relationship between sunlight, circulation, and storms remains complex. Uranus is also unusual because it gives off very little internal heat. Jupiter, Saturn, and Neptune all emit significantly more energy than they receive from the Sun, but Uranus releases only a small excess. This weak heat flow may explain why its atmosphere often appears less active than Neptune's. Despite the two planets having similar size and composition, the reason remains uncertain. A giant impact may have carried away internal heat, or rearranged the interior into layers that prevent warm material from rising efficiently. Composition gradients may keep dense and light materials from mixing, trapping heat deep inside. Whatever the cause, Uranus seems to conceal warmth rather than release it freely. Its magnetic field adds another layer of strangeness. The field is tilted strongly away from the rotation axis, and its center is offset far from the planet's center. As Uranus spins, the magnetic field sweeps through space in a lopsided pattern. The magnetosphere is compressed by the solar wind on the day side and stretched into a long tail on the night side. But because the planet itself is sideways, this tail can twist into a corkscrew shape. Charged particles become trapped and interact with the upper atmosphere, producing auroras in shifting locations. The field may be generated within a shallower shell of electrically conducting fluid made from water, ammonia, and other materials under pressure. This could help explain why the field is so irregular. Around Uranus lies a system of dark, narrow rings. They're far less reflective than Saturn's and contain relatively little fine dust. Many particles are darkened by radiation and mixed with carbon-rich material. The main rings are thin and sharply defined, suggesting that small moons help confine them through gravity. Some ring edges are shaped by shepherd moons, while collisions and impacts continually create and remove dust. The rings may be young compared with the planet, or may be repeatedly renewed from shattered moons. Their darkness makes them difficult to observe, and they were discovered only when they briefly blocked the light of a background star. The rings share the planet's equatorial plane, so they circle nearly vertically from the perspective of most planetary orbits. The major moons follow the same sideways arrangement. Miranda, Ariel, Umbriel, Titania, and Oberon are the largest, each a mixture of ice and rock, each carrying a different record of impacts and internal change. Miranda has one of the strangest surfaces in the solar system. Huge cliffs, ridges, grooves, and patchwork regions create a landscape that seems assembled from mismatched pieces. Early interpretations suggest that the moon may once have been shattered and reformed, but internal activity can create the observed terrain without total destruction. Tidal heating may have warmed the interior when Miranda occupied a different orbital resonance. Ariel appears brighter and smoother, with long valleys, fault systems, and plains that may have been resurfaced by icy material. Umbriel is darker and more heavily cratered, implying less recent renewal. Titania, the largest moon, displays great fault valleys and scarps that may form as its interior freezes and expands. Oberon, farther out, preserves an older cratered surface, though bright material on some crater walls hints at cleaner ice beneath a darkened exterior. Several of these moons may contain hidden oceans between their rocky interiors and icy crusts. Radioactive decay, residual heat, and compounds such as ammonia could keep water liquid at depth. The evidence is indirect, based on models and surface geology rather than direct detection. Yet the possibility expands the number of places where liquid water may persist far from the Sun. Uranus and its moons have been visited closely only once, when Voyager 2 passes through the system during the 1980s. The encounter occurs near southern summer solstice, when one pole faces the Sun and much of the opposite hemisphere remains hidden. The spacecraft discovers moons, rings, magnetic complexity, and a planet far stranger than its quiet appearance suggests, but it sees only one season and one viewing geometry. Much of Uranus remains poorly mapped, and its atmosphere, interior, rings, and moons continue to be understood mainly from distant observation and physical models. This limited knowledge leaves major questions open. The origin of the sideways tilt is uncertain. One immense collision could overturn the planet, but such an impact must also account for the regular orbits of the moons and rings. Multiple smaller impacts may produce the tilt more gradually. Gravitational interactions with other giant planets or a large ancient satellite may also alter the axis before the system settles. The present arrangement records the outcome but not the exact path. The moons may have formed after the tilting event from a disk of debris, or they may have survived and realigned through complicated dynamics. Uranus therefore stands as a reminder that planetary systems do not always preserve simple, upright order. A world can be struck, tilted, layered, and left with a family of moons that continues to orbit in the new plane. Its pale atmosphere hides vast winds. Its cold exterior hides dense fluids and perhaps trapped heat. Its dark rings trace a nearly vertical circle through space. Its moons preserve evidence of tides, fractures, and possible buried oceans. The seventh planet seems quiet only because distance softens its details. In reality, it carries the long after effects of an ancient event, still rolling through the outer darkness with its entire system turned towards a direction no other major planet follows. Neptune occupies the outer edge of the major planetary family, a deep blue world moving through sunlight so weak that noon there would resemble twilight on Earth. It lies nearly 30 times farther from the Sun than Earth does, and requires about 165 Earth years to complete a single orbit. Yet Neptune is not quiet. It carries some of the fastest winds known in the solar system, enormous storms that form and fade, a powerful magnetic field, faint rings, and a moon whose backward orbit reveals a history of capture and disruption. The planet is an ice giant like Uranus, but its atmosphere is more visibly active and its internal heat is far stronger. Hydrogen and helium dominate the upper layers, while methane absorbs red light and gives the planet its blue appearance. The colour is deeper than methane alone seems to explain, suggesting that other hazes or cloud particles influence the scattered light. Beneath the atmosphere lies a vast interior rich in water, ammonia, and methane under extreme pressure. These materials do not form familiar ice. They become hot, dense fluids, perhaps mixed with electrically conducting layers that help generate the magnetic field. Deeper still may lie a rocky core several times the mass of Earth, though the boundaries are likely gradual rather than sharply divided. Neptune receives very little energy from the Sun, yet it releases much more heat than it absorbs. This internal warmth rises through the atmosphere and helps drive violent weather. The contrast with Uranus is striking. The two planets are similar in size and composition, but Uranus emits little excess heat, while Neptune glows strongly from within. This difference may reflect how each interior is layered, mixed, or altered by ancient impacts. On Neptune, escaping heat feeds convection, lifts gases, and powers clouds and storms despite the distant sun. Winds can exceed 2,000 kilometers per hour. Some move eastward, others westward, depending on latitude. Because the planet rotates in about 16 hours, its atmosphere is organized into broad bands and powerful jet streams. Bright clouds of methane ice appear at high altitudes, sometimes casting shadows on lower cloud decks. Dark storms emerge as large vortices where atmospheric gases circulate around deep pressure systems. Voyager 2 observes the great dark spot during its flyby, a storm large enough to contain Earth. When later telescopes look again, that feature is gone. Other dark spots appear in different latitudes, proving that Neptune's larger storms are temporary even when they endure for years. Bright companion clouds often form near them, shaped by rising air and changing pressure. The planet's weather is dynamic on timescales short enough to be observed from Earth, despite a year lasting more than a human lifetime. Neptune's seasons unfold slowly because of its distant orbit. Its axis is tilted by about 28 degrees, close to Earth's tilt, so it experiences changing sunlight over the course of its year. Each season lasts more than 40 Earth years. Cloud patterns, temperatures, and brightness shift over decades. But the observational record remains brief. The planet has completed only a little more than one orbit since its discovery in the 19th century. Neptune is also a powerful magnetic world. Its magnetic field is strongly tilted relative to the rotation axis and offset from the planet's center, resembling the irregular field of Uranus. The field may arise in a shell of electrically conducting fluid where water and other compounds exist under pressure. As the planet rotates, the magnetic structure sweeps through space and interacts with the solar wind, forming a changing magnetosphere. Charged particles follow field lines toward the atmosphere and produce auroras, though observing them from such a distance is difficult. Around the planet lies a system of narrow, dark rings made from dust and small particles. Some rings contain brighter clumps known as arcs. At first, these arcs seem difficult to maintain because particles orbit at slightly different speeds and should spread into a uniform ring. The gravity of nearby moons, especially Galatea, helps confine the material through resonant interactions. The rings are faint because their particles are dark and sparse, and they may be renewed by impacts on small inner moons. Neptune's moon system is dominated by Triton, one of the most unusual satellites in the solar system. Triton is larger than Pluto and moves around Neptune opposite to the planet's rotation. This retrograde orbit cannot be explained by formation within a normal disk around Neptune. A moon born from such a disk would almost certainly orbit in the same direction as the planet turns. Triton must therefore have formed elsewhere and later been captured. Its composition and size link it to the icy bodies of the Kuiper Belt, the distant population beyond Neptune. In this sense, Triton may be a dwarf planet that became a moon. Capture is difficult. A passing object usually escapes or collides because gravity alone does not remove enough energy to leave it in a stable orbit. Triton may once have belonged to a binary pair of icy bodies. When the pair passed close to Neptune, gravitational interaction could have ejected one member while leaving Triton bound. Another possibility involves drag from an ancient disk or repeated interactions with Neptune's original moons. Whatever the exact process, capture must have redistributed enormous energy. Triton's early orbit was probably more elongated and tilted. As tides acted between moon and planet, the orbit gradually became nearly circular. During this adjustment, Triton would have disrupted the existing moon system. Some original moons may have been thrown away, driven into Neptune, or smashed together. The smaller moons seen today may partly be fragments or later survivors of that chaotic era. Triton's surface reflects its cold and active nature. Nitrogen ice covers large regions, along with frozen methane, carbon monoxide, and water ice. Few impact craters are visible, showing that much of the surface is geologically young. Broad plains, ridges, pits, and strange textures record movement within the icy crust. One famous region has a pattern compared with the skin of a melon, formed by processes that remain uncertain. Internal heating, overturning ice, and slow convection may all contribute. During the Voyager 2 encounter, dark plumes rise several kilometers above the surface and trail downwind through Triton's thin atmosphere. These geyser-like eruptions may occur when sunlight passes through translucent nitrogen ice, warms darker material below, and causes nitrogen gas to burst outward. They show that even under weak sunlight, the surface can remain active. Triton's atmosphere is extremely thin and made mostly of nitrogen, with traces of methane and other gases. It changes with the moon's long seasons. As sunlight shifts, nitrogen ice sublimates from warmer regions and freezes onto colder ones, moving atmosphere across the surface. Beneath the crust, Triton may conceal a subsurface ocean. Tidal heating during capture would once have been intense, and radioactive decay in the rocky interior may still provide warmth. Ammonia or other compounds could lower the freezing point of water. No direct evidence confirms such an ocean, but models allow it, adding Triton to the distant icy worlds where liquid water might survive in darkness. Triton's future is as dramatic as its past. Because it orbits backward, tidal interaction causes it to move slowly inward rather than outward. Over immense time, it may cross Neptune's Roche limit, where the planet's tides become strong enough to tear the moon apart. The debris could form a vast new ring system. This event lies billions of years away and depends on uncertain tidal behavior. But the direction of change is clear. Triton is not settled permanently. Its capture begins a slow path toward destruction. The planet and moon therefore form a system defined by order and instability. Neptune's gravity holds Triton close, but the backward orbit preserves evidence that the moon does not truly belong to the family into which it has fallen. The same gravity that captures it also brings it gradually toward a distant end. Beyond Neptune lies the Kuiper Belt, and Triton may be understood as a piece of that outer region pulled inward. Its frozen surface, volatile atmosphere, and possible hidden ocean connect the planet's moon system to the wider frontier of dwarf worlds and comets. Neptune stands at this boundary as the last major planet, but not as the end of the solar system. Its winds move faster than those of warmer worlds. Its storms appear and vanish beneath a dim sun. Its rings are held in delicate arcs. Its largest moon circles against the direction of planetary order, here, near the edge of the major planets. The structure of the solar system begins to loosen, and the calm geometry of familiar orbits gives way to a history shaped by capture, scattering, and the long memory of distant ice. Beyond Neptune, the solar system does not end with a clean boundary. It thins into a vast region of ice, dust, darkness, and slow orbits, where sunlight is weak and the paths of small worlds preserve the disturbances of ancient planetary migration. This outer domain includes the Kuiper Belt, scattered populations of distant objects, long-period comets, and the far greater but still hypothetical reservoir known as the Oort Cloud. Pluto is the most famous resident, yet it is only one member of a broad family of dwarf planets and frozen bodies. These worlds are small compared with the major planets, but they are not simple debris. They have mountains, plains, atmospheres, moons, internal layers, and histories shaped by heat that survives far from the sun. The Kuiper Belt begins beyond Neptune and extends across a wide band of space. Its objects are remnants of the cold outer portion of the protoplanetary disk, though many no longer occupy the places where they formed. Neptune's migration rearranges the region. As the giant planet moves outward, its gravity captures some bodies into resonances, scatters others onto elongated or tilted paths, and sends some inward toward the planets or outward toward distant space. Pluto occupies one of these resonances. It travels around the Sun twice for every 3 orbits completed by Neptune. This pattern keeps the two worlds from approaching dangerously close, even though Pluto's path is more elongated and inclined. Pluto is smaller than Earth's moon, yet its surface is one of the most varied known among icy worlds. Nitrogen ice spreads across bright plains, methane and carbon monoxide freeze in other regions, and mountains made from water ice rise several kilometers above the ground. At Pluto's temperatures, water ice behaves like rock, forming a rigid crust strong enough to support steep terrain. The most striking region is Sputnik Planitia, a broad basin filled mainly with nitrogen ice. Its surface is divided into large cells that appear to be renewed by slow convection. Warmer ice rises, cooler ice sinks, and the plain erases many impact scars. Glaciers of nitrogen flow around mountains and through valleys, showing that geology can remain active even where ordinary water is frozen harder than stone. Pluto's atmosphere is thin and seasonal. It is made mostly of nitrogen, with methane and carbon monoxide in smaller amounts. When Pluto moves closer to the Sun, surface ice sublimates and feeds the atmosphere. As the world moves farther away, some of that gas freezes back onto the ground. Haze forms in layers high above the surface, created when sunlight alters methane into more complex carbon-bearing particles. The atmosphere can expand, contract, and move frost across the planet over the course of its long year. Beneath the crust, Pluto may contain an ocean of liquid water, internal heat from radioactive elements, insulating ice, and dissolved compounds could keep part of the interior from freezing completely. Surface fractures and the shape of Sputnik Planitia are consistent with deep internal structure, though they do not provide direct proof of a present ocean. Pluto is paired with Charon, a moon unusually large compared with the body it orbits. Charon is more than half Pluto's diameter, and the two revolve around a shared centre of mass that lies outside Pluto itself. Both are tidally locked, so the same hemispheres always face one another. Charon's surface contains canyons, smooth plains, and signs of expansion, perhaps caused when an ancient internal ocean froze and forced the crust outward. The smaller moons move around the pair in complicated rotations, tumbling as their irregular shapes respond to the changing gravity of Pluto and Charon. Beyond Pluto, other dwarf planets reveal further variations. Eris is similar in size but more massive, moving on a distant and highly elongated orbit. Its discovery helps force a clearer definition of the word planet, and leads to Pluto's classification as a dwarf planet. Haumea spins so rapidly that it is stretched into an elongated shape. It possesses moons and a narrow ring, and it belongs to a family of icy fragments, likely created by a major collision. Makemake is bright with frozen methane and has at least one moon. Gong, Quaoar, Orcus, and many other large objects occupy the same broad frontier, some round enough to qualify as dwarf planets depending on how their shapes and internal structures are understood. Their surfaces differ in colour and chemistry because volatile ices escape at different rates. A world's size, distance, temperature, and impact history determine whether it keeps nitrogen, methane, carbon monoxide, or only water ice and darker organic residues. Farther out, Sedna follows an enormous orbit that carries it well beyond the main Kuiper Belt. Its path is too distant to be shaped strongly by Neptune in the same way as Pluto's. It may belong to an inner extension of the Oort Cloud, or it may preserve the influence of a passing star from the Sun's birth cluster. Other remote objects with unusual orbits have encouraged speculation about an undiscovered planet far beyond Neptune. No such planet has been confirmed. The apparent clustering of some orbits may indicate a massive distant body, but observational bias and the small number of known objects complicate the pattern. The outer solar system remains poorly surveyed, so both hidden worlds and misleading patterns are possible. Comets connect these frozen frontiers to the inner planets. A comet is a mixture of ice, dust, rock, and organic material left from early solar system formation. While far from the Sun, it can remain dark and inactive. When its orbit carries it inward, sunlight warms the surface and causes volatile ice to turn directly into gas. Escaping gas lifts dust and forms a glowing coma around the nucleus. Solar radiation pressure and the solar wind then produce tails that point broadly away from the Sun. A dust tail curves along the orbit, while an ion tail follows magnetic fields in the solar wind more directly. Short-period comets usually come from the Kuiper Belt and scattered disk. Gravitational encounters with Neptune and the other giant planets gradually redirect them inward. Long-period comets may come from the Oort Cloud, a distant spherical population extending far beyond the planetary plane. The Oort Cloud has not been observed directly as a structure, but the orbits of incoming comets strongly support its existence. Its objects may have formed among the giant planets before being scattered outward. Passing stars, galactic tides, and distant gravitational disturbances can then nudge some of them back toward the Sun. In this far reservoir, a single orbit may require thousands or millions of years. The Sun's domain also has a boundary defined not by gravity but by plasma. The solar wind expands outward and creates the heliosphere, a great bubble embedded in the surrounding interstellar medium. Far beyond Neptune, the wind slows at the termination shock. Beyond that lies the heliosheath, where solar particles continue to interact with material from between the stars. At the heliopause, the outward pressure of the solar wind balances the pressure of the interstellar environment. Voyager 1 and Voyager 2 cross this boundary and enter interstellar space, though they remain gravitationally connected to the Sun and still lie far inside the probable extent of the Oort Cloud. The heliopause is not a perfect sphere. It changes with solar activity and with the motion of the Sun through the galaxy. The solar system therefore has several endings, depending on what defines an ending. The major planets end at Neptune. The Kuiper Belt continues much farther. The heliosphere ends where the solar wind loses control. The Oort Cloud may extend toward the limits of the Sun's gravitational dominance. Even there, no wall separates the system from the galaxy. Objects can be lost, captured, or disturbed across immense time. The Sun itself travels around the centre of the Milky Way, carrying its planets through changing interstellar environments. Dwarf planets, comets, and distant icy bodies reveal that the solar system is not a simple set of 8 worlds arranged around a star. It is a layered structure with a dense inner region, giant planets, belts of remnants, captured moons, resonant populations, and fading frontiers. The farther the journey moves from the Sun, the more slowly everything changes, but the ancient history becomes easier to preserve. In the deep cold, small worlds retain volatile ices, old surfaces, and orbital memories that the warmer inner planets have lost. This solar system does not finish at its last planet. It dissolves gradually into the darkness, leaving behind a long trail of frozen bodies whose distant motion still carries the imprint of the beginning.